All right, everyone. So welcome to our very first Maverick content video. So let's recap a little bit about what exactly it is that we want to do when we talk about indefinite integration. So I picked a function for us to work with here in this video, and that is f of x is equal to negative x cubed plus 2x squared plus 2. And when we graph out that function, it looks a little bit like this. Got some fun curves to it, and then it keeps on going. When we do our integral, when we take the integral of the function, what we're doing is we are finding a function, so what we're going to spit out is another function with x's in it, that we can plug in numbers to get the area under the curve. So the indefinite integral is an equation. The definite integral is a number, and the difference there is the definite integral has defined boundaries. So let's say I want my boundary A to be here, my boundary B to be here. My definite integral from A to B would find the area under the curve from A to B to the x-axis, and that would be this area right here. So that's kind of the difference between indefinite integration and definite integration. They're remarkably related. You need to find the indefinite integral before you can even think about the definite integral. So we're going to work with this function in both this video and in the next, which is about definite integration. But first things first, how do we find the integral of this f of x? And this actually makes it a little clearer. It's a little hard to see. Now, to find the integral, I have some rules in my back pocket, similar to the rules that we have for derivatives. In fact, they're so similar because they are the reverse of our derivative rules. Now, in class, we gave these rules names based off of students in the class. We had Nelly's rule, Tempest's rule, Nico's rule, and Yonatan's rule. But since we're moving to Maverick, I'm going to go ahead and use the formal math names for those rules. That way, if you guys have more questions and want to seek out the greater internet to help you figure out what those rules are, you can. So to get myself prepped and ready to use my rules, the first thing we need to figure out is what exactly it is we want to do. Let's remind ourselves of our integration notation. So what I actually want to find here is the integral of f of x dx. Now, there are a couple of things of note here. The first is this symbol right here. This reminds me that I want to take the integral of. That's sort of how we say this. It's like a long, stretched out S. Actually, you can think of it as standing for sum. So that is going to be the first important part of my notation. The second important part of my notation is this dx right here. And that dx is sort of a bookend. We have the long S at the start of my integral, the dx at the back end of my integral. It serves a couple of purposes. If we had more variables than just x's, it would remind us which one we care about integrating. So things like multivariable calculus, this becomes super important. It's also a nice way to remind me when the function ends that I'm integrating. So in this case, I have my f of x above. So what I want to be doing is taking the integral of minus x cubed plus 2x squared plus 2 dx. So that is my goal. How do I do this? That is the question, and that is what we will be answering in the rest of this video. First things first, I want to figure out what happens if I take the integral of constants, because constants are something we're going to see over and over again in this function and in others. And in this function, we're dealing with constants in three separate places. We have the secret negative 1 here before our x cubed. We have the 2 before my x squared. Even this extra 2 is a constant because we can think of this as being 2x to the 0, because x to the 0 is just 1. So all three of my terms have constants in them, so knowing how to work with constants is going to be super duper important for integration in general. So my rule for working with constants when I take the integral is going to be exactly the same as the rule I had for constants when I took the derivative. So if you remember way back then, you already have this skill in your toolbox. It's just about adapting it to a new medium, to the integral. So let's generalize this and see what happens when I take the integral of some constant k times f of x dx. Now, this constant k could be any number. It could be 2, it could be 700, it could be 12,000, and this f of x can be any function. It can be x squared, x cubed, e to the x, the log of x, sine of x. Any function at all is going to have the same rule. And the rule here says that when I take the integral of k f of x dx, this is actually equal to k times the integral of f of x dx. So all I've really done here is booted out my k. It's now outside my integral, meaning that I can sort of reserve that constant, keep it over there, do the integral of the function, do the tricky part of my integral, and then just multiply my constant back through. So I can kind of keep it on reserve, hold it over by itself, and then when I'm ready, I can kick it back in and continue my multiplication. So that is my first super useful integration rule. My second super useful integration rule is going to be what happens when I am adding or subtracting various terms together. And these are going to be called the sum rule and the difference rule. And these are even the same names that these rules have when we are talking about derivatives. Same names for integration. So again, if you remember back to when we did derivatives, it's going to be super useful to bring that knowledge back here. So in this case, let's take a look what happens if I take the integral of f of x plus g of x dx, or in the case of the difference rule, the integral of f of x minus g of x dx. Now, if I do this, much like when I take the derivative, I can think of these two functions as separate. I can think of them as f of x and g of x uniquely, meaning I can do the integral of f of x plus the integral of gx dx, and that looks like this. So I have the integral of f of x dx plus the integral of g of x dx. Same thing for the difference rule, the integral of f of x dx minus the integral of g of x dx. Same functions, same d of x dx, just a little bit different and laid out a little bit differently. So what that looks like above is you can think of this guy as my f of x, this guy is my g of x, and this is maybe an h of x or some other function. So I can just take the integral of each of these three pieces separately, add them back together, and I'll find the function I ultimately want to take the integral of. So for right now, those are the rules that matter for us. This is as far as we got in class. So it's as far as I'm going to go in this video. And it turns out that these are all of the rules we need to take the integral of my example f of x. So at this point, let us take a look at what the So what this looks like in the function above is we can think of this as being three separate functions that we've added together to make my greater f of x. So we can think of this guy as f of x, this guy as g of x, and this is maybe an h of x or some other function. But I can take the integral of each of these guys separately, add them back together, and find the ultimate integral of the function as a whole. So that's what my sum and difference rule are telling me. Again, should be super familiar because they look exactly the way they did for derivatives. We have one more rule we need under our belt before we are able to take the integral, and that is going to be the power rule. And this is another rule that has the exact same name as a derivative rule because this guy is the inverse of our derivative rule. Meaning that this guy is going to be exactly the same, but backward. So if we were to take the derivative of a function, we would use the derivative power rule. Then if we wanted to get back to the original function, this is sort of how we undo that work. So let's generalize this out and see what happens if I take the derivative of x to the n dx. So sum x to some power dx. When I do that, it's important to keep track of this n right here because that's the n that I care about. This is going to be equal to 1 over n plus 1 multiplied by x to the n plus 1 plus some constant c. So if you guys remember, whenever we do an integral, we always have this plus c. It's important to just keep that in the back of our minds. So because in this generalized example, we are solving the integral in our example, it's important to have that plus c in there. And you can see my n shows up right here, 1 over n plus 1, and my n shows up over here with n plus 1. So if we can remember our three rules that we have going on here, I have my constant rule, I have my sum and difference rules, and last but not least, I have my power rule This will set us up for success in integration. And in fact, these are the only three rules that I need to solve the function up above to take the integral right here. So I am all set and ready to do that. And that's what we're going to be doing next. So I'm going to go ahead and clear some of the stuff we have here. So please make sure that you're taking notes. This is a great spot to pause the video if you'd like, so that you can figure out sort of what you have written down already. Take a sort of take stock of what you understand and don't understand, and feel free to reverse this video, rewind a little bit if you would like. But I'm going to go ahead and solve my example.